Greetings, everybody. Learning is a hobby here. I want to go through my summary of section 5.2 in Tao's Analysis 1 book here. So let's do that. We'll continue constructing the machinery that we need to construct the real numbers, which will be done in section 5.3. So let me bring up my summary. And we'll just go through it. Okay, so starting with the definition. We defined what a Cauchy sequence was last time. Now we want to define what we mean by epsilon close sequences. So this is definition 5.2.1. Let AN and BN be two sequences and let epsilon greater than 0. We say that the sequence AN is epsilon close to BN if and only if AN is epsilon close to BN for each N and N. In other words, sequence A0, A1, A2, ... is epsilon close to the sequence B0, B1, B2, ... if and only if the distance between AN and BN for all natural numbers N is less than or equal to epsilon. Right, he gives an example here to, again, flesh out the concept. The two sequences, 1, -1, 1, -1, 1, ... and 1.1, -1.1, 1.1, -1.1, 1.1, etc., are 0.1 close to each other. Note, however, that neither of them is 0.01 steady. So there's, I guess just pointing out the difference between the two concepts. So okay, definition 5.2.3, eventually epsilon closed sequences. Let AN and BN be two sequences and let epsilon greater than 0. We say that the sequence AN is eventually epsilon close to BN if and only if there exists a natural number capital N greater than or equal to 0, such that the sequences AN and BN are epsilon close. In other words, A0, A1, A2, ... is eventually epsilon close to B0, B1, B2, ... if and only if there exists a capital N greater than or equal to 0, such that AN minus BN, the distance between AN and BN, is less than or equal to epsilon for all N greater than or equal to capital N. All right, he has a remark here that he mentioned this before, but it's worth, I guess, saying again. The notions of epsilon closed sequences and eventually epsilon closed sequences are not standard and will not be used outside of the section. All right, so once we develop, the notion of limits and stuff, we won't need these more primitive concepts. Example 5.2.5, the two sequences 1.1, 1.01, 1.001, etc., and 0.9, 0.99, 0.999, etc., are not 0.1 close, but they are eventually 0.1 close. The two are also eventually 0.01 close and 0.001 close, and so on and so on. All right, and that leads us to the definition of what we mean by equivalent sequences. So this is definition 5.2.6. Two sequences, AN and BN, are equivalent if and only if for each rational epsilon greater than 0, the sequences AN and BN are eventually epsilon close. In other words, A0, A1, A2, ... and B0, B1, B2, ... are equivalent if and only if for every rational epsilon greater than 0, there exists a capital N greater than or equal to 0, such that the distance between AN and BN is less than or equal to epsilon for all N greater than or equal to capital N. All right, so if that's the case, then we say that the two sequences are equivalent. All right, that'll be important when we start talking about equivalent Cauchy sequences. He has another remark here that he labels 5.2.7. As with definition 5.1.8, the quantity epsilon greater than 0 is currently restricted to be a positive rational rather than a positive real. However, it's really not going to make a difference whether epsilon ranges of the positive rationals or the positive reals. And he says see exercise 6.1.10, which is, the next chapter. So we'll look at that when we get around to it. Another remark, the following proposition in decimal notation asserts that 1 is equal to 0.999 repeating forever. And he says, see proposition B.2.3. We'll look at that appendix at some point. I think I'm going to hold off on doing appendix B until after we look at sequences in series. So that'll be, a little bit down the line. All right, proposition 5.2.8, let AN and BN be the sequences AN equals 1 plus 10 to the minus N and BN equals 1 minus 10 to the minus N. Then the sequences AN and BN are equivalent. So we'll prove that here. Let epsilon be greater than 0, be an arbitrary positive rational number. Then the distance between 1 plus 10 to the minus n minus and 1 minus 10 to the minus n is equal to 2 times 10 to the minus n for whatever n is. And then we actually need a couple of lemmas here. Lemma 1 is he states these in the proof in the book, but he asks you to prove them. So let mn be natural numbers such that m is less than n, then 10 to the minus m is greater than 10 to the minus n, and the proof is by induction. So let m be less than n, then there's a d in n minus 0 such that n equals m plus d, and we induct on the number d. So here's the base step: d equals 1, 10 to the minus n equals 10 to the minus m plus 1 equals 10 to the minus 1 times 10 to the minus m, which is obviously less than 10 to the minus m. So the base step is satisfied, and same thing holds in the inductive step. So if we assume that 10 to the minus m is greater than 10 to the minus m plus d for some d in the natural numbers minus 0, then consider 10 to the minus m plus d plus 1. That's 10 to the minus 1 times 10 to the minus d, 10 to the minus m plus d, which is less than 10 to the minus m plus d, which is less than 10 to the minus m, and that shows that the theorem is true. That follows by the inductive hypothesis, obviously, right? Okay. Lemma 2 is that is this statement here: let n be a natural number, n greater than or equal to 1, then 10 to the n is greater than or equal to n. He asks you to prove it in the proof, but I skipped it just because it's virtually identical to my solution to exercise 4.3.5. So just look at that exercise, and just all you have to do is replace 2 by 10, and it works. So now we can prove the proposition that those two sequences are equivalent. By lemma 1, if n is greater than or equal to n, then 10 to the minus n is less than or equal to 10 to the minus capital N, which implies that 2 times 10 to the minus n is less than or equal to 2 times 10 to the minus n, which is less than 2 over n by lemma 2. Then choose n greater than or equal to 0, such that 2 over epsilon is less than or equal to capital N, which we can always do by proposition 4.4.1. And then for any n less greater than or equal to capital N, the distance between the nth term of the two sequences is equal to 2 times 10 to the minus n, which is less than 2 over capital N, which is less than or equal to epsilon. Sorry, just give me 1 second, guys. Okay, sorry about that, everyone. We're almost done here. So that's the proof. So therefore an and bn are eventually epsilon close for every epsilon greater than 0. So the sequences are equal, and that's the last bit in this section. So let me just stop the screen share. Like I said in the last video, section 5.1 and 5.2 are actually kind of short. So are their exercise sets. So I'll get to the exercise set in the next video, and then the next section where we define the real numbers is actually kind of long, so I might have to hold off on that because I got some things coming up, so I might have to get around to that next week. But anyway, I'll end the video here, and I'll see you guys in the next one. So keep learning, guys.